Hello, this is Xing. Today I'll be explaining how recursion connects to mathematical induction, and we'll see it in an example of a sorting algorithm. So first, let's start by recalling what a mathematical induction is. Mathematical induction, also known as proof by induction, is a mathematical techniques to prove a property or statements on some discrete domains. That is something that is countable, like natural numbers or integers. It goes as follows. To prove something, you want to first proceed with its base case. The base case will be on its countable domains. The smallest step of, say, n equals 1 or n equals 0, depending on the context. If this is held true, if this statement is held true at base case level, then you proceed with inductive step. To do so, you first have a inductive hypothesis. That is, you assume that the statement is held true for some k, some smaller k less than n. So assume this being true, and our job is, with our inductive step, to prove that this also holds true for k plus 1. So the next or the larger steps. If we can prove both base case and inductive case holds true, then the statement must be true. How it relates to recursion then? Well, suppose we want to write a sorting algorithm. Let's just call it sort. It will take in an input of an array. So say we have an array, just for the sake of example, 3, 1, 4, 2. Of some length n, in this case n will be 4. So let's name it A. This is we have an integer array A, and then with length n. Okay, the base case is trivial, so it's when we have a trivial array of just 1 or 0 elements. What happens when you are sorting a array with just 1 element or no elements? You are done. You are done sorting. So you return. You're done with this algorithm. What if we're working with larger arrays, say like this array of length n, this big array of length n? So remember, the big picture is, if you can prove something, the tiniest little parts works and the smaller parts, like some k less than n works, then you can prove this for the entirety of the array. In this case, let's say we want to have some smaller subarrays, that's not the entirety subarrays, but also greater than the base case. So let's split this one in half into a left array and a right array. And our inductive hypothesis would be, we assume that our sorting algorithm magically works on the leap phase for the subarrays of the left array and the right array. And by doing so, we will see that the entire array after merge would work as sorted. So that is basically saying our inductive hypothesis is sort works on some n is in half. And by doing so, our algorithm goes, we sort the left array, and then we sort the right array. Of course, you will want to divide this left and right array by, say, first defining a midpoint, call it mid. Midpoint goes from beginning to the mid, or from mid to the end, and name it otherwise. But here, just pseudocodes, we call them left and right. So now we know that our assumption is that left array sorted and right array sorted. Proof by inductions tell us, if you just merge these two sorted left and right array together, then the final picture would be this array is sorted as accordingly, 3, 2, 1, 4. And that is how mathematical inductions will relate to sorting. And this is what we call a recursion. During this process, when it's split into half, it also split into half and then split into half again into 3, goes to our base case. And when it keeps on doing it, eventually you're gonna receive a final picture.